Now, after EAN, we will try to understand the geometry in coordination compound. Now, many theory is put forward to explain the geometry and bonding in coordination compound, namely VBT, that is valence bond theory. It is very similar to the valence bond theory in covalent compounds with slight difference. Other theories are ligand field theory, crystal field theory, and molecular orbital theory, that is MOT. However, before doing any of the theories, first we need to understand that coordination compounds or complexes are generally observed in these four geometries, that is linear, square planar, tetrahedral and octahedral. Now, when there will be two ligands attached to the central metal atom, it is generally linear in shape and the hybridization is sp. Yes, hybridization, the orbitals will be mixed and recasted. In this case, there will be two orbitals, one s and one p, that will be mixed and recasted. This one is different from hybridization in covalent compound. There the hybridization was of unpaired or half-filled orbitals. Here the hybridization will take place of empty orbital. This is the only difference between the two. Again, your one s empty and another p empty orbital will mix and recast to give you two sp hybrid orbitals. Similarly, if the ligands are 4, it can be either square planar or tetrahedral. If the hybridization is dsp2, you can count 1d, 1s and 2p, so that makes up 4. Or it can also be sp3, s1s and 3p, that again makes up 4, but the structure is different. When the hybridization is dsp2, the coordination compound appears to be square planar. The angle between the ligands is 90 degree. However, when the hybridization is sp3, the complex appears to be tetrahedral. The angle is 109 degree 28 minutes. Now, if there are 6 ligands attached to the central metal ion, then the geometry will be square bipyramidal or also known as octahedral. There will be 4 ligands in one plane and there will be 2 ligands on the axial plane. Hybridization of this octahedral complex can be D2sp3 or sp3d2, which we will be learning in the upcoming slides. Hybridization in coordination compound is the easiest topic. Just you need to remember some few basics. The first thing that you need to remember is the hybridization and the geometry. If there are two ligands sp linear, if there are 4 ligands dsp2 square planar, or if it is 4 ligands sp3, then it's tetrahedral. If it is 6 ligands, it will be octahedral. Another thing that you need to remember while doing hybridization in coordination compound is spectrochemical series. Now this is a series where we have arranged the ligands in the decreasing order of their strength, like CN or NO2 minus or EN or pyridine. These are strong ligands, while the halides I minus, Br minus, Cl minus, F minus are the weak ligands. Now, how are CN minus, ammonia, ethylene diamine, or even carbonyl, CO? These are strong ligands, and why are they strong ligands? You will understand this in crystal field theory. However, in this particular video, we will just remember that carbonyl, that is CO, CN minus, ammonia, ethylene diamine, these are considered to be strong ligands. They are strong ligands. While halides, that is F minus, Cl minus, Br minus, are weak ligands. This is something that you need to remember. The reasons will be understood in crystal field theory. However, this is something that you need to remember right now. Another thing, another basic that you need to know is the electronic configuration of the metal. The central metal can be anything, but mostly it is a D block metal, and you are supposed to know the configuration of the central metal. For example, if it is scandium, then it's 21, it's 3D1 4s2. If it is titanium, it is 22 3D2 4s2. You can see the entire configuration. You can pause the video and you can see the entire configuration of scandium to zinc over here. There are only two exceptions, which is chromium and copper, which shows abnormal electronic configuration. Chromium is 24, so it should be 3D4 4s2, but because of more stable half-filled orbital, one electron is transferred to 3D from 4s. So it becomes 3D5 4s1. Similarly, copper should have been 3D9 4s2, but it is in reality 3D10 4s1, again for more stable, completely filled d orbital. So these are the three things that you need to remember. If you will remember this, the hybridization part becomes very simple. Let us start with the hybridization. We will simultaneously do two examples. One is NiCl42 minus and the other one is NiCN42 minus. Now both over here has 4 ligands, and when they have 4 ligands, I'll go back to the slides. If there are 4 ligands, so it can either be a square planar complex or it could be a tetrahedral complex. Now as both one had Cn and the other one had Cl, Cl is a weak ligand while Cn is a strong ligand. Both have nickel, so nickel is 3D8 and 4s2. In fact, the oxidation state of both the central metal atom is same, which is Ni plus 2. The oxidation state is plus 2. So let us see how does the hybridization change for the two complexes, which is exactly identical. So here you have the electronic configuration of nickel, which is argon 3D, argon 3D8 and 4s2. Now we know there is 2 electrons that has to be lost, because there are the oxidation state is plus 2. So in order to form that compound, nickel has removed 2 of its electron, and that is basically done. So here the central metal is nickel, which is 4s2 and 3d8. Now the oxidation state is plus 2, so it has to lose 2 electrons, and always remember the 2 electrons are lost always from the outermost shell. So 3d is inside and 4s is outside. Okay, so always the electron will be lost from the outermost shell, that is the electrons will always be lost first from 4s and then 3d. So 2 electron nikalne, so 2 electrons will be removed from 4s. So the configuration of nickel 2 plus becomes 3d8, 4s0 and 4p0. Now this is the same case for nickel Cn4 minus. Again your nickel is a central metal, so it is going to be 3d8 4s2. 2 electrons will be lost from 4s, that makes nickel 2 plus 3d8 4s0. Now what you need to remember, or what you need to understand, is that in cyanide is a strong ligand, and what cyanide is going to do is cyanide will force the 2 unpaired electron to jump and get paired. Because it is a strong ligand, it will force the last electron to move forward and get paired. Now you need to understand, for hybridization we need empty orbitals, because the ligands are going to donate 2 electrons. Now in both the cases there are 4 ligands, so each ligand is going to donate 2 electrons. So there is a total of 8 electrons that is going to be donated, and hence we need 4 empty orbitals. Because if there is 4 empty orbitals, each empty orbital can accommodate 2 electrons. So 4 ligands can donate 8 electrons in 4 empty orbitals. Now both the ligands are going to make space for that empty orbital. Now cyanide, as it is a strong field ligand, it will force the unpaired electron to jump inside. So that will make 3d8 paired, completely paired. The electron will be jumping inside, and one of the 3d orbital will become completely empty. So the hybridization over here is going to be 1d, 1 4s and 2 4p. Again I'll repeat, we needed 4 empty orbitals for hybridization, as there were 4 ligands and each ligand were going to donate 2 pair of electrons. So over here, one empty orbital was taken from D. I am talking about NiCN4. So one empty orbital was taken from D, because cyanide, being a strong field ligand, had paired the 2 unpaired electrons. So the hybridization over here is DsP2. However, chlorine is weak, it is poor. So it doesn't have that power that it will force the electron to jump and get paired. So there will be no jumping in the weak field electron, in the weak chlorine electron, in the weak chlorine ligand. There will be no jumping over here, and hence the hybridization will be 1s and 3p's. Here there is no empty d orbital available. In CN4 there was an empty d orbital available, because Cn forced the electron to get paired. However, Cl cannot do that. So because of this, there is change in the geometry, as the hybridization in NiCl4 is sp3, as there was no d orbital available. So the geometry becomes tetrahedral in NiCl4, and it has 2 unpaired electrons. So as it has 2 unpaired electrons, it is called as, the complex will be paramagnetic. That is, it will be attracted in the magnetic field. While in NiCN4, as Cn was a strong field ligand, as the electron got paired, the hybridization became dsp2, and the geometry now for NiCN4 is square planar. And hence, as there are no electrons left, it will be diamagnetic, that is, it will be repelled in magnetic field. So see, there is very slight difference. The difference in the 2 complexes was only of ligands. Both had central metal atom as nickel +2. However, in one example we had a weak field ligand, and in another example we had a strong ligand. Because of the strong ligand, the hybridization became dsp2, and because of the weak ligand, the hybridization becomes sp3. The only thing that you need to understand over here is, if there will be a strong ligand, there will be jumping, there will be pairing, if necessary. If there is a weak field ligand, the weak field ligand will not be able to move the unpaired electrons, and hence the hybridization will be of the outermost orbital. Again, I will repeat that over here, the hybridized orbital will be the empty orbital. Unlike in covalent compounds, here we need empty orbitals to be hybridized, as ligands are going to donate 2 electrons and not 1. As you can see in the last line of the diagram, that 4 pair of electrons from Cl minus, 4 pair of electrons from Cn minus. So these were the 2 examples. We will move to the next example. Here there is a diagrammatic representation. NiCl4 is tetrahedral, while NiCN4 is square planar, both being very similar. Let us see some more examples. Let us see some examples of some example of octahedral complex. So again, I will be going with octahedral complex with a weak field ligand and with a strong field ligand. So